Live. Hello, everybody. Good evening. Welcome to our second part of our 8-part series where we're going to be reviewing all the topics you need to know to pass the AP Physics 1 test, coming this May. We're just going to double check we've got everything all squared away on the technical side before we get into this. So I'm just gonna really quickly pull up the stream on my phone, make sure we don't have any weird audio artifacts going on. Yeah, and as soon as we get that all squared away, we can get going. All right, I can hear myself. There's a slight delay. That's about what we'd expect. I'm gonna turn that off because we don't want to hear an echo. I don't want to hear an echo. That's gonna drive me crazy. Yeah, so let's get on to what we're looking at today. So today we're going to be dealing with dynamics, and dynamic means motion, he said, accidentally moving his entire thing. Let me get my cursor on the right window. That would help. Okay. Yeah, and so dynamics are going to be objects in motion, but a little bit beyond kinematics. We're looking at how this applies with Newton's second law. So Newton's second law being, of course, the rate of change of momentum is proportional to acceleration. No, is proportional to the net force. But that's what that's really telling us, though. If we have a change in momentum, that's usually just going to be a change in velocity for constant mass. So that a change in velocity is acceleration. So we can write our mass times our acceleration, this is the rate of change of momentum, is going to be our net force. So typically, I mean, we can think of this just generally for a single force. If we push on an object with some mass m, it will accelerate with magnitude of the force divided by the mass. But we include this net term here because sometimes we'll have, in fact, most times we'll have multiple forces acting on our objects at once, and so we have to take the net force in the direction that it's going. We'll see some forces cancel out, some forces only partially cancel out, and we'll have components that don't, and that is going to be the motion that we're looking for today. So let's just get started. This is, again, just kind of a roadmap for what we're looking at in the future. We have done kinematics. We've taken a look at that. You can go back through our YouTube channel. These are uploaded. I think they're also on Twitch. Also, you can look through our kinematics if you have any questions. Any questions throughout the stream at all tonight, feel free to type them in the chat. I have the chat window up to my left, so it's not quite on my eye line, but I'll be turning to it fairly regularly to keep track and make sure that you guys are understanding what I'm going on about. And so today we're going to be dealing with this guy, dynamics. So let's just begin with some multiple choice practices. We'll see what these questions look like in context and look at the strategies after as we go. So we've got a ball of mass m suspended from two strings of unequal length as shown above. Magnitudes of the tensions T1 and T2 must satisfy which of the following conditions? So we don't actually need to calculate these. We just need to relate these two tensions, see which one would be greater than the other. And so if we think about our mass here, we've got some T2 pulling up this way and some T1 pulling up this way. And then there's a downwards gravity force. So I actually often use like a subscript notation. So I'd write force sub t, like F sub t for force of tension, like this. But you get these are kind of some old school problems, and so they like to use the capital letters. You can see it down here too. I'll probably actually just stick with the subscript notation, but we'll try to make sure that that doesn't get confusing. I think this is a much clearer way of expressing things too, because eventually there are other values we want to use that have a value of g or t, and so it's kind of unwise to keep reusing those letters. But subscripts are always good. And so this is at equilibrium, so that means all its net forces are balanced. So that means all our downwards forces are balanced with their upwards forces, and all the forces pulling to the right are balanced with all the forces pulling to the left, which I know is a mirror image for you guys, so trust me, I know my left and right. It's just, yeah. So what we can do then is we can break apart these two into components. We can say that this has an x component and a y component, such that this would form the edges of a right triangle. And same for this guy here. And we start to see now that this is not to scale because the left side here, the x component on T1 is much larger. And but we don't expect that to be any larger because the only thing balancing it is the x component on T2. And so if this has equal x component, so this goes further over, but it has a higher vertical height than the hypotenuse of this triangle, and we're comparing this vertical height relative to this horizontal line, the hypotenuse therefore has to be larger. So that tells us that we expect T2 to be greater than T1. We can kind of think about this intuitively too. The mass is like more underneath T2, so it's kind of taking more of the load. The tension is higher. Cool. So for these next problems, we're looking at a block sliding down a 30-degree incline with some acceleration of 2 meters per second. And so to start with, we want to show what is the free body diagram that represents all the forces acting on us. They use W for gravitational force, which is kind of gross, but we expect gravity to always be pointing downwards. So right away, we can rule out A and C. Because these are pointing down in the rotated frame of reference, which we'll discuss a bit more in the FRQ section. But for even when we rotate our frame of reference, we expect our gravity force to be pointing downwards. But now, taking a look at the normal force, that's going to be this force N. Normal force is the force exerted by a surface from an object resting on that surface. This is an artifact of Newton's third law. Every force has an equal and opposite reaction. So the action of gravity pressing down on a surface gives us the reaction of the surface pressing up on our object. And so normal here means perpendicular. This is where that term is referring to, or you might have maybe heard of like the norm of a vector. That would be like the perpendicular. And so let's see if I can remember how to spell perpendicular. There we go. So we expect this to be perpendicular to our surface. And our surface is at a 30-degree angle. So D satisfies that, B does not. So this gives us D is going to be our correct answer. Just taking a look for funsies, the last force we had to satisfy was the friction force, and that's going to be pointing in the opposite direction of motion. So if we're going downhill, we expect to be pointing up the slope, which actually works for both B and D here. But D has all the conditions that we want, so D is going to be our choice. And so we want to find out then, now, which of the following correctly indicates the magnitudes of the forces acting up and down the incline. So we expect we are moving down the incline with some force. So this would be the x component of gravity would be what is driving us in this instance. Again, we'll discuss this a bit more once we go into the FRQ section. For multiple choices, we want to kind of focus on moving through these quickly. And then there's a friction force opposing us. And so our net force in the direction of motion is, I mean, we don't even need to discuss what these forces are because we're just asked about if they're up the plane or down the plane. So down the plane is our gravity. That's the direction of our motion, so we're going to make that our positive value. Opposing our direction of motion is our force up the plane. And that is going to equal our mass times our acceleration. Now we know our acceleration. Our acceleration is 2 meters per second, and we know our mass, that's 2 kilograms. So we expect this to meet the condition of this must equal 4 newtons. We have a net force of 4 newtons pulling us down the hill. So right away we can rule out ones. So these all have a gap of 4 newtons, but we expect the 4 newtons to be, well, okay, so B doesn't. We can rule that out. C does have a gap of 4 newtons, but that's got the 4 newtons moving up the plane. We want the 4 newtons moving down the plane. And so we're between A and D now. And so we have to then consider which both of these choices satisfy this condition. But the other condition that needs to satisfy, we can consider what the force down the plane might be. And so this x component of gravity, I guess, yeah, this is a good time to go over this. So we have our object on our slope here. And we think of our gravity going down. But if we orient our reference frame to the direction of motion, we have, this is our x direction aligned with the 30 degrees, and our y direction is perpendicular to that. And so we can then break up this force of gravity into two components, just like we did up here, only now these components are aligned with our 30 degrees. And so this x component is the force driving us downwards. And so the force driving us downwards is then going to be equal to, so this ends up being our 30-degree angle on the top, and this is opposite that. So the sine relation relates, so sine of 30 degrees gives us our opposite over hypotenuse. This opposite is our FGX, or our force down. And our hypotenuse is just the force of gravity, Fg, or mass times gravity, mg. And so that means our force down has to be mg times the sine of 30. Now I believe sine of 30 is 1/2, but I'm going to double check because, yep, it's 1/2. Okay, now I feel silly, but that's fine. So we have 1/2 times our mass, which is 2, times g, which we can approximate to 10. So we have 20 times 1/2 is our force down the hill, which is 10. So D ends up being our best choice here. Cool. So any questions so far? Looks good so far. Let's keep on moving. We've got the frictionless system shown above, so there's no friction acting on these blocks, is accelerated by an applied force of magnitude tension in the strings. What? An applied force of magnitude F. I think that they're just missing a letter F here. I think that's a typo. And then F, comma. The tension in the string between the blocks is, so what's the tension between these here? So let's look at our two forces here. Our two blocks. Our first guy only has this force of tension. This is what we are looking for, by the way. We want the magnitude of this force. And that's accelerating at the same rate as this other guy. This other force here has the same force of tension pulling backwards on it. This is our 2 kilogram mass. This is our 1 kilogram. And then we have the applied force pulling out this way. And so for both of these cases, we expect them to be moving at the same acceleration a. And so our first object is just moving due to some f of t is equal to its mass, 1 kilogram, times this acceleration, which we don't know, but we'll just write as some a. And then we want, and then for our second object, now we have a net force going on because we have our force F minus the force of tension that's pulling it backwards. And that's going to equal the mass of this object times its acceleration, which is the same acceleration. So what we can do is we can take this, solve this for A, and plug it in. We can actually do this either way. In fact, actually, this one might be a little bit easier. We can plug in a value for A and then solve it for f of t. Two equations, two unknowns. We're just using algebraic substitution. This is a very common technique in physics. So we're going to get A on its own here, and our acceleration is this force of tension divided by 1 kilogram. So let's plug that in here. And so we have the equation then that our force F minus an f of t is equal to, we have 2 kilograms times plugging in for A, f of t over 1 kilogram. So the units kilograms cancel out. So we have 2ft minus ft equals f. So we can add ft to both sides, and we get f is equal to 3ft. And then getting ft on its own, we just divide both sides by 3, giving us ft is equal to 1/3 of f. And so that looks like that's going to be option D here. Any questions so far? Looks pretty good. Looks pretty good. Alrighty, running out of space a little bit on here. It's okay. If we do run out of space, we'll just make an extra page. On the actual test, you will have as much scratch paper as you need. Number 5, we're asked about a ball falling straight down through the air under the influence of gravity. There is a slowing force, we don't really use that word anymore, on F, with magnitude given by some constant b times its velocity. And so the ball reaches a terminal velocity after time t. So what is the magnitude of the acceleration at time t over 2? So when we are falling, we have a ball. We're gonna write this up here. Oh no, we can't see it up there. We'll draw this down here. Can you see that? Yeah, that's good. So we're falling. We have a downwards force due to gravity. This is going to stay constant, right? Because this is only due to mass times acceleration due to gravity. Neither of those things are changing. What is changing, though, is the magnitude of this drag force here. And so this drag force is slowing us down, but it's increasing because as we accelerate downwards, our velocity increases. And so this gets larger and larger until eventually Fd will equal Fg, and then we will be in an equilibrium. We will be no longer accelerating. And once we reach that point, that is what we call our terminal velocity. So at time t over 2, so halfway between when we reach our terminal velocity and when we start, we expect our acceleration to be decreasing, because we would start at 10 meters per second, but as we pick up more velocity, we're getting slowed down by the air around us. We're decreasing from 10 meters per second squared down to 0 in a apparently linear way for this type of drag force. We will see eventually, well, not at this level, but in college physics, you can see there's actually quadratic drag that goes like d squared. And so that won't increase linearly. But again, we're not going to be dealing with that at this level. That's more for once you want to start messing with like Lagrangians and things like that. Yeah, cool. Looks good. So next we are looking at a block with some weight W. When they say weight, we're referring to the gravity force, not the mass. It's pulled along a horizontal surface at a constant speed v by some force F. This force is being pulled up at an angle theta with a horizontal, just like in the diagram here. So only some component of this is actually contributing to our velocity. Some component is just pulling up. The normal force exerted on the block has a magnitude, so if we weren't pulling up with a rope, it would have a magnitude equal to W, because we would expect the only forces acting on this block in the vertical direction to be the force of gravity, the weight, and the normal force, our Fn. But in this case, we also have the y component of this guy. That's as we're pulling on this rope at an angle, we're lifting it up a little bit. We're taking a little bit of pressure off the surface. And so we see that our normal force goes less than W. And so B is going to be our best choice here because we expect it to be greater than 0. It's not going to be, we're not lifting it off the ground. If we are no longer touching the surface, then it goes to 0. But it's going to be less than W because it is less than that equilibrium point because we're adding a non-zero force. Cool. Any questions? Nope. Looks good. Looks good. All right. Next, we've got a uniform rope of weight 50 newtons hangs from a hook as shown above, and the box of weight 100 newtons hangs from the bottom of that rope. What is the tension through the rope? So that's, I haven't seen a mass rope in a while. So what we've got acting on here then, this rope has got, the further up we go, the more mass it has to take. So at the bottom here, the tension is the force pulling us upwards here, and it's only lifting up the mass of this box, right? This is our force of tension here. So at the bottom, this is just going to be 100 newtons. However, at the top now, when this is connected here, this has to also carry the 100 Newton box, but then the weight of this rope, the extra 50 newtons. And so D is going to be our best option. As we move up, the tension gets higher and higher, but it starts at 100 at the bottom because it's just holding the box, and then it's 150 at the top as it has to then hold its own weight. So moving on to number 8 now, we've got an object hanging from the center of a massless string, and the tension at any point in the string. So, okay, so we've got the same string. Okay, yeah, center of a, so, oh, are we gonna get a weird, we might get a weird double in here. If this is off by a factor of 2, we have to be careful. So our tension in the string, we're kind of coming in here. We've got a force of tension pulling up this way and a force of tension pulling up this way. We expect the y components of each. So these two y components are going to be equal because this is symmetrical, right? These are both centered around some angle theta from the middle. And so these two equal y components, we'll call these FTY. We expect 2 FTY to equal our downwards force, our weight. Again, I usually like to write this as FG, but they keep using W, so I'm just going to stay consistent with the problems to keep things a little bit more clear. And so we can then find the... So we can solve for FTY because we know this is going to equal our weight. I mean, what we can see this is coming from is if we add up our net forces in the y direction, we have a positive 2 FTY, and then a negative W is equal to our mass times our acceleration in the y. But because we're being held in equilibrium at rest, this goes to 0, so that term goes to 0, meaning we can add W to both sides, giving us this relationship here. And so we can get FTY in terms of W. FTY is equal to W over 2. And then we can relate FTY to FT. So FT would be our hypotenuse here. So we can use inside angle theorem. And so this is a little bit goofy here because my drawing gets a little bit strange. But if we look at this version, this is the one drawn to scale. Our triangle is this guy. And so inside angle theorem tells us that this top angle is going to be theta here. And that comes from, well, inside angle theorem, but you can, another way you can think about this is the sum of all triangles is 180 degrees. So that means this angle has to be complementary to that. And then if this has to be complementary to theta, and then this top angle meets the ceiling at a 90-degree angle. So this complement plus this mystery angle adds up to 90 degrees. So this has to be the complement of that complement, which is theta again. And so we then get FTY is adjacent to that. So the cosine relation, cosine of theta, gives us our adjacent over hypotenuse. And we know our FTY, we want to get FT. And so to get FT, we will multiply both sides by FT and divide both sides by cosine. So we get FTY over the cosine of theta. Plugging in for FTY, we have that as W over 2. So our FT in one of these is W over 2 cosine theta. And you might think that we are done because this looks very good. This is one of our options, although I think there's a trap here. First of all, there's no C, which is strange. That's the first time I've noticed this. But this is only the tension in one of these. And if this is the same string that is suspended in the middle of, like we have one string that's attached here, it runs through and goes back up, it's feeling the tension from both sides at once. So the actual tension at any point in this string is double this, because we have two pieces of this holding up our string. And so that's then going to be this times 2, which is E, which is the fourth one instead of the fifth one. Again, I don't know what, they just missed C somewhere. Yeah. Cool. Moving right along here, we've got a little diagram for number 9 here. A block of mass 3m is going to be moving frictionless on a horizontal table, and the block is attached to another block of mass m that's running over a pulley. And if we drop mass m, it's going to start to fall downwards and pull the mass 3m along with it. And we want to know what is the magnitude of the acceleration of the descending block. So to do this, we're going to write a pair of free body diagrams. And I'm going to do this up here because I kind of ran out of space at the bottom there. And so we've got our 3m block. Technically, we have a gravity force and a normal force, although that's actually not going to affect us in this problem because there's no friction, so we don't need to do anything with that. And then we have a tension force. And so this is going to be accelerating in this direction at the same rate of acceleration as our little mass. But our little mass is moving in a different direction. It's moving down. So that's what the pulley does. The pulley is able to redirect this force. So the Newton's second law equation we get from this is Ft is equal to our mass times acceleration, and our mass is 3m. And then A is unknown, but A is what we want to solve for. But we don't know what this Ft is yet, so we can't really solve for it. But to get this Ft, we then just have to look at our little m. Is that still visible? Good. I know part of the screen is blocked out by my face over here, on this side. Here, my face. And so I don't want to get covered up by any of that. Anyway, back to our second block here. This is accelerating downwards due to gravity. Gravity is pulling it along, but it's being opposed by this tension force. Tension force is pulling it upwards, but it's going to be lesser than gravity because we expect that we're going to be accelerating downwards. And so again, we're going to align our coordinates with the direction of motion, which in this case is downwards means positive. In this first case, we had to the right was positive. And so this equation then would be Fg, our force in the positive direction, minus Ft, our force in the opposite direction. Oh, that looks kind of goofy. Can we get a nicer T there? There we go. Is going to equal its mass, which is just 1m, times A. And so what we can do is we can then take this Ft, the Ft's are the same due to Newton's second law, and plug it in there. I'm going to kind of move this down this way. We have Fg, which I'm going to plug in as mg, minus 3ma. And that is equal to ma. So we want to get acceleration on its own, but we want to get all our accelerations together first. So we're going to add 3ma to both sides. So we get mg is equal to 4ma. And then we can divide both sides by m, cancels out. And we divide both sides by 4. We get our acceleration is equal to g over 4, which is a. Cool. Moving right along, we've got another inclined plane problem. It's a 3, 4, 5 triangle. Look at that. 3 squared plus 4 squared equals 5 squared. You can try that one out in your head. We've got a block with weight 20 newtons is placed at the top of the plane and allowed to slide down. And so that means we have a force pulling straight down this way. This is our weight, but I'm still going to use it as Fg because I'm stubborn like that. And so we're asked about the magnitude of the normal force. And so to check out the normal force, we want to look at our reoriented, ooh, that's a really gross line there, our reoriented coordinate system. And so if we have our x direction be moving down the slope and our y direction be perpendicular to the slope, we expect our normal force to be at this perpendicular. And so, because we also don't expect any motion in the y direction, because that would involve either the block floating away or tunneling into the thing, into the inclined plane, we expect these forces to be balanced. We expect the forces to be balanced in the y direction. And so that means the y component of our gravity, if we then now draw our gravity as components aligned with our new coordinate system, this y component here, FGY, is then going to be equal to is equal to our normal force. Now, this tells us that our normal force has to be less than 20 newtons because we know our gravity force is 20 newtons, and that's the hypotenuse of our triangle. And the hypotenuse of a triangle is always going to be larger than the legs, unless the angle is 0. And then it's not really a triangle anymore. It's just 2 lines. And so FGY is the leg of the triangle that's smaller than FG, and Fn is equal to that. So we expect this to be less than 20 newtons, but greater than 0. We don't expect this to go to 0 because it is still touching the surface. All right, 11 is a multiple correct one. I kind of hate these, but that's fine. We've got 3 forces acting on an object. If the object is moving to the right in translational equilibrium, which of the following must be true? So, translational equilibrium, the vector sum of the 3 forces must equal 0. That is true. If we are in equilibrium, that means the forces are balanced. They're not going to be accelerating. So that is true. All 3 forces must be parallel. That's not true. We can have forces going perpendicular as long as enough forces balance each other out. Then, no, yeah, this doesn't have to be true. I was thinking about, so the fact that yeah, I was gonna say the fact that there's 3 kind of made me think, oh, well, I can't think of a way to have one go this way and one go this way, and then add a third that isn't in either one of these directions, because then if I add this one, it's no longer in equilibrium. But that's actually not the case, because they don't all have to be like that. I could have one big one going this way, and then I could have 2 off at angles, like this. So their x components cancel out, their y components cancel out. We reach translational equilibrium, but we're still in motion. So B does not need to be true. C definitely does not need to be true, especially because we got 3. It's actually very unlikely that these would all be the same magnitude. But we do know that the acceleration must be 0. And so if we are moving to the right, we can't be accelerating. So that means we must have a constant speed. So A and D are our 2 choices that we would like there. Cool, cool. So, 12 asks us, for which of the following motions of an object must the acceleration always be 0? So it's not simple harmonic motion. We'll get into that later, but it's basically constantly accelerating. Any motion in a straight line? No, we can have acceleration in a straight line. We just think of like a drag racer. Think of driving a car off of out of a red light. You accelerate in a straight line. You can have non-zero acceleration. Motion at a constant speed, that is gonna have an acceleration of 0, because our speed, our velocity, the rate of change of velocity is acceleration. And so if our acceleration is 0, the velocity or speed must be constant. And then D seems plausible because it's like, oh, well, if our velocity is not changing, our momentum has to stay constant. But remember that our momentum is mass times velocity. And so most of the time, we only really look at this change in velocity. But there are cases where the mass can change. A good example of this would be launching a rocket. Because as a rocket flies through the air, it's jettisoning fuel and burning off its different rocket fuels and oxidizers. It's changing its mass. And so it changes its momentum as its mass changes, as well as when its velocity changes. So D is also not going to be an appropriate choice. So C is going to be our best answer here. All right. So we've got a rope of negligible mass supporting a block that weighs 30 newtons as shown above. The breaking strength of the rope is 50 newtons. So the largest acceleration that we can give to this block by pulling it up without breaking the rope would be what? And so if we pull this upwards, that means that we have some upwards force of tension acting on this. And we know that if this tension becomes greater than 50 newtons, this breaks. So let's find out what we reach at that limit there. At 50 newtons, what is the highest that we can get to? And so we'll look at our net forces here. We have a force of gravity pulling us downwards. That's the weight of 30 newtons. And then, oh, actually, let's have a look at this. There's a better way to phrase that, but I'm not bothered by it. Let's actually reorient our coordinates so that moving upwards is positive, because that is going to be the direction of our acceleration. And so what this actually gives us, we actually want our ft to be positive, not our fg. Again, this actually doesn't really matter, but if we had it the other way around, we'd get a negative value for our acceleration, and I don't like dealing with too many extra negatives. It's very easy to accidentally cancel one or forget to cancel one, and then you end up getting the completely wrong answer. So it's generally a good rule of thumb to approach, orient your coordinate system along the direction of motion. So that way, whichever direction you are accelerating in is your positive direction. So this is going to equal our mass times acceleration. And so now we're going to look for the limit at when ft equals 50. So we'll have 50 newtons minus 30 newtons is equal to, what was our mass? Well, so our mass, if we estimate g is 10, our mass would be 3 kilograms because our gravity force is 30 newtons, and 3 times 10 is 30. And then this is our acceleration. Acceleration is what we want to find. So we're going to get acceleration on its own by dividing both sides by 3 kilograms. 50 minus 30 is 20 newtons, divided by 3 kilograms. 20 thirds is like about 7. Yeah, it's going to be 6.7 meters per second squared. I know I estimated that from 21 divided by 3 is 7, and so we expect this to be a little bit under 7, and then we just looked at our available answers, and only one of these fits that criteria. We do have access to a calculator, so we could have calculated that, but this ended up being a little quicker, although then with the explanation, it really wasn't. Awesome. All right, so questions 14 and 15 are using the same thing, but 15 is on the next page, so we might need to jump back and forth a little bit here. We've got a horizontal uniform board of weight 125 newtons and a length of 4 meters supported by vertical chains on each end. So let's get a little image of what we've got going on here. We've got some board, and then we've got vertical chains. It kind of looks like springs. That's, you know, there's like chains. It looks like a swing. And a person weighing 500 newtons is hanging on the board. So we've got a downwards weight. Let's call this FGB. This is the force of gravity due to the board. And then we'll call this FGP, force of gravity due to the person. And then we know, no, I guess we can write those next to it. This is 125 newtons, if I can write as I speak. Apparently not. And then this is 500 newtons. We are told the tension in the right chain is 250. So we want to know, what is the tension in the left chain? So if this is being held at equilibrium, we expect the upwards forces to equal our downwards forces. And so our downwards forces, we have our FGB plus our FGP, our two weights, and that has to be balanced by our tension forces, our two forces of tension, one on the right and one on the left. Now we know the magnitude of the one on the left, so the one on the right has to follow this, fill this gap. FGB is 125 plus FGP is 500, giving us a total downwards weight of 625 newtons, and that is equal to, our force of tension on the right was 250, plus our FTL, which is what we want to find. So we'll subtract 250 from both sides, and that's going to give us, so subtracting 50 is 575, 200 off of that is 375. That's going to be our option C. So C is our best choice for this guy here. So let's, any questions? Looks good. I mean, any viewers? It's okay. We had viewers coming in after for this past one, so we're just gonna keep on trucking here. Which of the following best describes where the person is hanging? So if we have an unbalanced thing like this, and we're gonna see that my drawing wasn't that accurate. So let's label these in red so we can see them clearer. If we have this side, it has a magnitude of 250 newtons, and this side has a magnitude of 375 newtons. This one is taking much more tension, so this is having more weight on it. So that means our person is going to be closer to the left. And so what are our options here? Between the chains, but closer to the left chain, between the chains, but closer to the right chain, right in the middle, or directly below one of the chains. We don't expect to be directly below, because then that would be taking all 500 newtons of it, which isn't what we're seeing. So it is between the chains, but we do expect it to be closer to the left side because that had the higher tension. Good. All right, so now taking a look at 16, I think. Is this our last multiple choice one? This is our last multiple choice. We are just cruising. Actually, we're making pretty good time. So we have a cart of mass 10 kilograms, shown above, moves without friction loss on a level table. 10 Newton force pulls the cart horizontally to the right. At the same time, we have a 30 Newton force at an angle of 60 degrees above the cart. Pulling up at that angle to the left. So we wanted to know which of the following would describe the manner in which this cart is moving. Okay, so let's find out where our net acceleration is. We have, just going in the horizontal direction, we have a positive 10 newtons this way, and in this direction, so we know we have 30 newtons up here, but we want the horizontal component of this, which is going to be this guy. And so that's closed by the 60-degree angle, and so this is adjacent to that angle, so we can use the cosine relation. So the cosine of 60 degrees relates us to, so we want to know this magnitude of force F, right? So that relates us to this force F. I guess we can call it Fx, because it's the x component of the force. It's moving us in the x direction. Divided by our hypotenuse, which is 30 newtons. So then to get the magnitude of Fx on its own, that's going to be 30 times the cosine of 60 newtons. And I should probably know the cosine of 60. I think it's actually half again. It's half again. Okay, so our Fx is 15 newtons. So we have a net force to the left of 5 newtons. F net equals 5 newtons to the left. So that means we are accelerating to the left. But this is multiple correct, so we have to kind of keep wily about what could be happening. We like the case of moving to the left and speeding up. That is what accelerating to the left means. But we could also be moving to the right. We could have had some initial velocity to the right, and then we're accelerating to the left. And so if we're accelerating in the opposite direction, that would be slowing down. So D is our other option that is correct here. We could have some rightwards velocity, and then this acceleration is slowing us down. Good, good. We've got two people are pulling on ends of a rope. Each person pulls with a force of 100 newtons. The tension in the rope, well, so if we've got a rope here, someone's pulling it this way with 100 newtons, and someone's pulling it this way with another 100 newtons. The rope is being stretched by 200 newtons. Yeah, just adding them together. All right, and so 18, we see a graph of speed as a function of time. This is growing kind of like a parabola, right? So it's growing like an x squared type of a slope. In fact, yeah, look at that. It is proportional to t squared. I'm just reading things out loud, apparently. Which of the following graphs best represents the magnitude of F for the net force of the object as a function of time? So we expect F is going to equal ma, and our mass is constant throughout time. So this isn't really going to affect our graph here, but our acceleration is the rate of change of our velocity. So our velocity is increasing at an increasing rate. Our rate of change is going up at a constant rate. And so that would be then proportional to something like a here, because this is a linear behavior. Another way we can tell, if you're comfortable with calculus, this would be the derivative, and the derivative of t squared is t, which is a line. Linear graph has to be a. But this is the non-calculus course, so we just want to think about these in terms of rates of change. You can kind of have a derivative in the back of your head if you like, but we want to be able to do these just without having to resort to using calc. Yeah, so I think that actually does it for our multiple choice problems for today. Any questions so far? We're looking pretty good. I'm going to grab a quick thing of water. Shoulder's a little sore. My second vaccine shot this morning. Very exciting, although still have a sore shoulder, so there's that. All right. So now, this is kind of an exciting one here. We've got 3 blocks all connected by ropes, and we've got a pulley system going on, but 2 of our blocks are sitting on an inclined plane. So we have to reorient our coordinate system and then think about how these are acting on each other. There's a lot going on for this here. Yeah, masses m1 and m2 respectively connected by a light string shown above. These blocks are further connected to mass m, passes over a pulley, negligible mass of friction, so we don't need to worry about torque. And they're moving downhill at a constant velocity. So they're not accelerating, but they are moving downhill. So we expect this to have some sort of kinetic friction. And they had some angle theta and kinetic friction F and 2F. Okay. So let's have a look at all the forces on block 1. So block 1 has a gravity force. It's just pulling straight down here. It has a normal force pointing up this way. It's going to be perpendicular. We have a tension force pulling us up this way. That's from the rope attaching it to M2. And then we have one more. It's our friction force, and that is just from the surface of the ramp, slowing us down a little bit. So next, we're asked to find the coefficient of friction between the inclined plane and block 1. So the coefficient of friction shows up in our relation for friction force. Where can I write this? Let's go up here. No, we'll do this over here. I want to make sure this is going to be a complicated one, so I want to make sure we'll have space for everything. So our friction force, we expect to equal mu times our normal force. And we want to express this all in terms of m, m1, g, theta, and f. Oh, wait. Really? We know f? Well, that is much easier then. So, okay, if we know the friction force has magnitude f, we can solve for mu by saying it is just f divided by Fn. That is our mu. But Fn is not in terms of these units we want to use. So we need to then see what that force is going to be. And to do that, we now need to break up our Fg into components. We get, and so this is, to do this properly, what we're doing is we have our coordinate system aligned with our direction of motion. It's our first thing we want to do. You then follow your coordinate system like you're moving through like city blocks. So I'm going down the y and then over in the x. I could also go over in the x and then down in the y. I actually end up drawing equivalent triangles here. Just by habit, though, I tend to prefer drawing the triangle on the bottom, but it's personal preference. And so this angle theta is going to be the angle on top here. If we want to really quickly prove that, we can draw a line down here connecting this to this. This gives us a right angle down here and a complementary angle up here. Let's call this like beta. And then this comes in at a perpendicular angle FG, this y component of FG. See, now I'm a little bit annoyed that I moved this FG down here because that's just hard to see. FG would be on this side, right? That's our hypotenuse pulling us downwards. Our FGY is going to be at 90 degrees with this slope. So beta plus theta has to equal 90 degrees. Sorry, beta plus this mystery angle has to equal 90 degrees, but beta plus theta is 90 degrees due to them being complements from this original triangle. Therefore, this top angle is our angle theta. So FGY is adjacent to that angle. We get the relation that FGY over FG, which I'm actually going to go ahead and plug in the definition over MG, M1 technically, is equal to our cosine of theta. And so to get FGY on its own, FGY is equal to M1G cosine of theta. Now this is useful because when we take our Newton's second law in the y direction, we have a positive Fn and a negative FGY. And that is on this direction, in this perpendicular motion, we don't expect any motion in that direction because we're not floating off the thing, we're not tunneling into the ramp. So the acceleration goes to 0, so the mass times acceleration goes to 0. We can add FGY to both sides, showing us that our Fn, our normal force, is equal to the y component of our gravity. So our normal force is equal to m1g cosine theta. And then that gives us all the way back down to this mu here. We know our F, and divided by our Fn, which we wrote as m1g cosine theta. This is all in terms of these guys. Oops, these guys here. Good. Alrighty. So C is where things get a little bit tricky now. We want to determine the value of the suspended mass m such that this allows blocks 1 and 2 to move with constant velocity down the plane. So let's take a look at what's happening on m here. We have some force of gravity pulling it downwards. This is going to be big M times g. Big M is what we're looking for. And then there's some force of tension. Let's call this Ft2 because this connects us to block 2. And so if we have constant velocity, that means our acceleration is 0. So that means that Ft2 is equal to mg. Let's hold on for that now, and now let's take a look at what's going on for block 2. Block 2 has Ft2 pulling it up this way. It has some force of gravity of its own. I guess let's plug in our m2g. We can just write it in right away. That's fine. We also have a friction force that was 2F. And we have a normal force. Our normal force being, just Fn. And so we want our acceleration in the x direction, which is down this way. Well, the acceleration is going to be 0 again because our velocity is still constant, but we want our motion in the x direction. And so that we'll take our Newton's second law by adding up our net forces in the x direction. And to do that, we need to then break up this into components. The x component for this guy is down the slope, so that is opposite our angle theta, meaning that's going to be the sine relation. So we have down the slope, we have an m2g times the sine of theta minus our ft2 minus a 2f, and that is equal to 0. So if we want, we can rearrange that to bring the negatives over, but let's leave it for now because we're gonna be doing a lot of rearranging at the end here. And then that brings us down to our last guy here. And we have our free body diagram down here. It's a little bit of a mess, so let's just take a quick look at what we've got going on, at least for the x direction. We've got our friction force F. We've got our tension force. We'll call this Ft1. Oh, I missed Ft1. Yeah, there was also an Ft1 up here. That's in the positive direction. So let's add that. If it's on the positive side, I'm going to add that over here. Can we see that on the thing? Oh, this is like a really bad spot to be writing those, isn't it? Oops. Let's rewrite this whole equation somewhere else. Can you guys see down here? Oh yeah, down here's great. So okay, let's rewrite the equations of motion for our net force for block 2. So we have Ft1, this is the force of tension connecting it to mass 1. We have m2g times the sine of theta. This is the x component of gravity pulling us down the hill. And then pulling us up the hill, we have Ft2. This is the tension connecting us to mass big M. And then we have our friction force, which is 2F. And this is all going to equal 0. Good, good. And then we want our equations of motion now for our last block here. And so this only has gravity pulling it down the hill. That's going to be an m1g sine theta. Pulling it up the hill is Ft1. And also our friction force F. And that's all going to equal 0. So let's start this, I guess, by taking this equation of motion for our first block, for block 1, not the first block that we did this for, that guy there. We're going to rearrange this for Ft1. And so what we'll do is we'll add Ft1 to both sides, and then we're done. So we have Ft1 is equal to m1g sine of theta minus our F. How are we looking on time? Pretty good. If this goes a little too long, I do have a student after this, so I will have to cut it off early. But we're looking pretty good on time for now, so I'm not worried about it. But just a heads up. And so now we can take this and plug this in here. So we then get m1g sine theta plus, I'm going to put the m2g sine theta here, but don't forget this little f. I just want to keep these next to each other because it'll make it easier when we combine these terms. We're going to make this easier on ourselves. We have that minus f. We don't want to forget that. We have a minus ft2, and then we have a minus 2f. And this is all equal to 0. So bring this back around. We're kind of running out of space. That's fine. You know, if we run out of space, we'll just get another page for scratch paper. That's totally fine. So let's factor out the g sine theta out of both of these terms here. Let's move all our negative stuff to the opposite side, and we'll combine our f's. So we'll have m1 plus m2 in a quantity times g sine theta is equal to, we have our ft2, we added that over to this 0 side here, plus 3f. Looks good, looks good. And so now we want to get, and now we can plug in this relation here. Oh, I want to do that with the laser pointer. Yeah, laser pointers are cool. We know what our ft2 is, and it's in terms of our big M, which is what we wanted to solve for, right? We're still looking for mass M. So this side is equal to big mg plus 3f. So we want to get big M on its own. And so to do that, we'll minus 3f from both sides. So we'll have m1 plus m2 g sine theta minus 3f is equal to big mg. And then to end it, we're just going to divide both sides by g. Cancel that with that. And we have the sum of our masses times the sine of theta minus 3f. And that is all in terms of our m1, our m2, our g's, our thetas, and our f's. Look at that. So we'll leave it like that. All right, let's see. You reckon we'll be able to squeeze d in this tiny little corner here? Let's give it a try. If we don't, we'll just get a new page. It's not. So now the strings between blocks 1 and blocks 2 is now cut. Determine the acceleration of block 1 while it's on the inclined plane. So we can take our equation of motion for block 1. That was this guy here. This is now going to be missing that ft1 term. So we can rewrite this without that ft1. We have this as m1g sine of theta minus f. It's not going to equal 0 anymore, though. It's going to equal our mass times our acceleration. We expect this to be accelerating. We want the acceleration. And so that's going to be our mass, which is m1 times a. And we want to get a on its own, so we'll just divide both sides by m1. It cancels out on this term, so we get g sine theta. It doesn't cancel in this term, so we have f over m1. And that is equal to our acceleration a. Good, good. Any questions on any of that? All right. Looks good. Yeah, this one looks scary, looks messy, really not that challenging if we can just express our different equations, our different rules of motion. These are Newton's second laws, and then we just started plugging them into each other. Again, we also want to use Newton's third law to know which tension forces correspond to the same equations, because this was how we substituted them in. Cool. And so we're going to see a lot of these types of problems are shorter. We have these short style, just because the FRQ portion of the test they're not all going to be very long. Some of them are just going to be like, we'll see this is not going to take very long here. And yeah, this is a good option for dynamics, because dynamics is not a terribly complicated subject. This is honestly probably as bad as it can really get, beyond then having to include other topics like circular motion or something. Yeah, so we've got a helicopter holding a 70-kilogram package suspended from a rope 5 meters long, accelerates upwards at a rate of 5.2 meters per second. So we know the acceleration, we know the mass, we know the length of the rope, although I don't think we really need that, but that's fine. And so, oh, no, we do need that. Yeah, that's going to be for part C. So we've got our downwards force is our force of gravity, and our upwards force is going to be the tension in the rope. And that's it. That's all the forces acting on this object. It's just a rope dangling from a helicopter. Something like, can we draw like a little... Something like that. Yeah, look at that. Little helicopter. Very nice. All right, we want to determine the tension in the rope. So we expect, if we are accelerating upwards at a rate of 5.2 meters per second, upwards is our positive direction. So we'll have, that's a plus, not a T. Oh, that looks even worse. Let's just draw like a normal human being. Nope, I think that might be impossible. Close enough. So we expect our upwards force of tension, minus our downwards force of gravity, to equal our mass times our acceleration in that direction. We know this acceleration. We want to get Ft on its own. And so to do that, we'll just add Fg to both sides. Ft plus F, oh, sorry. We don't want the plus there. The plus is going to be on the other side of the equals. Is equal to ma plus Fg, but we're going to plug in the definition of Fg, which is mg. And so that's going to equal, we can factor out our mass if we want. We've got 70 kilograms. times our acceleration, which is 5.2, plus g. Are we asked to use 10 for g? We're not, so I'm going to go with 9.8 because 9.8 is cooler. Actually, and that works out much nicer because then it is just 15. So our force of tension is 70 times 15, which I do still need a calculator for. 1,050. 1,050 newtons is equal to our force of tension. Yeah, very cool. So that's B, all done and dusted. And so now, when the upwards velocity of the helicopter is 30 meters per second, the rope is cut, and the helicopter continues to accelerate upwards at 5.2 meters per second squared. Determine the distance between the helicopter and the package 2 seconds after the rope is cut. So, how do we want to do this? So our distance, we can think about from the perspective of the helicopter. So we'll see how much further away this object is getting. This is now a kinematics problem. We have some acceleration. Oh, we are missing an equals sign. Equals our acceleration, which is going to be g. All right. Technically, this is g is a negative number. We'll keep that in mind. We have the upwards velocity, and so this would be the helicopter moving upwards. We can think of that from the perspective of from the perspective of the helicopter, the object is moving down at that velocity too. So I guess we'll give that a negative 30 seconds. Well, okay, let's get our general formula here, and then plus some y offset. And that offset is going to be the length of this rope. So we have g, negative 9.8, pointing us downwards. Vy is going to be also moving downwards from the perspective of the helicopter. If the helicopter is moving up at 30 meters per second, the package has an initial velocity of down 30 meters per second. So we have this is, and this is then going to give us a negative number, by the way. This is going to output the distance below the helicopter that this is. And so the distance part is just the absolute value of that. So that's just going to, we'll just turn it positive. So we have negative 9.8 meters per second squared times, we want 2 seconds after this. So our t is going to be 2. 2 seconds squared plus our velocity we said was a negative 30 meters per second times 2 seconds. And then we have a y offset. It started, again, if this is below us, we want to make this a negative value. This starts out 5 meters below us because of the length of the rope. So we can just combine all these together. And also, I guess worth mentioning too, we got this 9.8 meters per second because as soon as we cut the rope, tension goes away, and our force of gravity is equal to our mass times acceleration. That gives us A is equal to G, and A is then 9.8. That's because the rope is cut, this force of tension now goes away. We don't need to worry about this 5.2 at all. Oh, just kidding. We totally do, because the helicopter is still moving it up at 5.2. So they're separating at a rate of 5.2 plus 9.8, which is, again, 15. So those are in opposite directions. They're splitting up quicker because helicopter's going up, package is going down. That I'm glad I went over that because I would have totally missed that. Okay, so let's see what we can do without a calculator. 2 squared is 4. Divided by 2 is 2 again, so we have negative 30. That's meters. Minus 30 times 2 is 60. Minus 5. This is going to be 95 meters below after it falls, after the rope is cut. Cool. Again, nothing too challenging. I got a little bit weird on part C. In hindsight, there might have been a wiser way to do this if we'd have done this from the perspective of the box, but then we would have had to, I don't know, we would have had to then factor in our motion downwards as being added on to the helicopter's acceleration. Either or, we're just thinking about our reference frames. We want to think about how far apart these are relative to each other. Good. Oh, this is an old one. 1976. Yikes. They have elevators back then? Okay, so we've got two guide rails on this elevator. That's these guys here, and they each exert a constant friction force of 100 newtons. When the elevator is moving upwards, so if it's moving upwards, the friction force is pulling down, both of which have magnitude of 100 newtons. When the elevator is moving upward with an acceleration, that is when it's moving upwards with a net acceleration of, well, any acceleration, because it is going to be net by definition, of 2 meters per second squared. And so we have a counterweight. This is our force of tension is what's pulling us up here. We also have a force of gravity. This is due to that 400 kilogram mass. Oh, this is, okay. Yeah, this is what part A was. I probably should have read far enough ahead to realize I should draw it on this guy. So these are our two friction forces. We know their magnitudes. They're 100 newtons each, but we're just going to label them like that. We have our gravity force, also pointing down, but from the center of mass. And then we have our tension force pulling us upwards. And this, not quite drawn to scale, because we actually expect this to be greater than all of them, because it is overcoming all three of these to accelerate us upwards. So calculate the tension in the cable lifting the 400 kilogram elevator. So if we're moving upwards at 2 meters per second, Ft will be our positive value. Then we have a negative. Our friction forces are the same, so I'm just going to write them as 2F, 2FF minus our Fg. That's going to equal our mass times our acceleration. But we know our acceleration, so we can solve for this by just rearranging this guy. So our Ft is going to equal our mass times acceleration, plus, let's do this Fg, which is going to be our mass times gravity, plus this 2FF. Now, in our terms, this is 400 kilograms times our acceleration upwards is 2 meters per second squared. I'm going to factor out the n, so we can just combine this with g here, which is 9. Oh, nope, not 9.8. It asks us to use 10. 10 meters per second squared, excuse me, plus 2 times 100, which is 200 newtons. So 400 times 12 plus 200, I kind of can't do that in my head. I could with time if I had nothing else to do. It's 5,000. Okay, yeah, no, that was an easier. Oh, no, I don't want to listen to myself. That's even worse. Pulled up the calculator, fumbled to the calculator, and then opened up the Twitch screen, so I had to listen to my own voice. I don't know how you guys do it. Cool. And so, yeah, what do we say? 5,000 newtons? Good, good. Tension in the spring. Again, pretty straightforward stuff. FRQs for this section aren't going to be that challenging. We now want to calculate the mass of the counterweight, the mass that this counterweight must have to raise the elevator with an acceleration of 2 meters per second squared. This really isn't that difficult either, though, because our counterweight only has two forces acting on it. It has its gravitational force pulling it downwards, and the tension force, which is the same as the one we just calculated, because it's the same rope. And the pulley has negligible friction and mass, even though look at the size of it, it's massive. But yeah, it's still infinite mass, or zero mass. So yeah. And so our Fg is big M times G. And so we want this is going to move downwards as our elevator moves upwards. That's the nature of a counterweight. And so we have our force of gravity, big mg, minus our f of t is equal to our mass times our acceleration. Now we know our acceleration is also going to be at 2 meters per second squared. We know our magnitude of f of t. It has to be the same as this guy. And we don't know our big M. So let's get our m's all on the same side, and then yeah, get them together. So I'm going to minus big MA over here, and I'm going to add FT to both sides. So we get mg minus MA is equal to FT, a positive FT, because we added it to both sides, so it canceled out with a negative one here. Now we can factor out the m, and so we have big M times g minus a is equal to ft. And then for our last piece, just to get m on its own, we're going to divide both sides by g minus a. So in our context here, that is 5,000 newtons divided by 10 meters per second squared minus 2 meters per second squared, so 8 meters per second squared. 5,000 divided by 8, I should probably be able to do that. So 5,000 divided by 4 is going to be 1,250. Yes, yep. And then therefore divided by 8 would be half of that, which would be 625. Yeah, so that's going to equal 625 kilograms. And you know what? Just to be safe, we'll run that through a calculator. It's so easy. It's not going to take us long at all. 625. That's what we call self-doubt, children. You shouldn't have that on the test. Be brave. Be courageous. All right, this is actually going to be our last problem for tonight here. We are making great time. This is kind of a short section. Yeah, the challenging portions would be our pulleys and our inclined planes, and so we kind of took a look at how like the worst that could really get to. But yeah, then we'll see other problems like these, but these are going to be much simpler, you know. So we've got a simple pendulum with a bob of mass 1.8 kilograms attached to a string of length 2.3 meters. The pendulum is held at an angle 30 degrees from the vertical by a light horizontal string attached to a wall, as shown above. So we've got, let's draw our free body diagram. I was about to draw it up here, but then I realized that's actually what the first problem wants us to do. So let's just draw it here. And it's really easy. We've got a tension force pulling up the rope here. Let's call this T1. Doesn't really matter. Then we have a separate tension force holding us to the side here. This is F of T2. And then for our last piece, we have our gravity force. That is Fg. So we are now asked to find the tension in the horizontal spring. We want to know what is Ft2. And so if this is in equilibrium, which is what it is because it's being held in place, held still, we expect all forces in all different directions to be canceling each other out. But we have forces kind of all over the place, right? We have some going straight down. We have one going straight down, one going horizontally, and then one going off at 30 degrees. And so let's take this 30-degree one and split it up into components. So we'll go along the x direction. We have an x component to our tension. And then we go up the y direction. And we have a y component to our tension. We'll call this Fty, and this one Ftx. I'm going to, at this point, omit calling it, referring to these as T1s, because this is the only one that breaks into components. But just know these are referring to T1. Yeah, and so we expect now our Newton's second laws in our x and y directions to be balanced, meaning that our acceleration goes to 0. Our upwards forces are equal to our downwards forces. Our rightwards forces are equal to our leftwards forces. And so we have in the vertical, let's start with the vertical. We have our Fty minus our Fg. Our Fg is the one we can calculate because we know our mass and we know our length. Do we need the length? We might need the length. We'll see. I don't think we'll need the length, actually. That might just be a non sequitur. This is going to equal 0. This is our Newton's second law equation in the y direction. Now we'll do a Newton's second law equation in the x direction. We have a positive Ft2 pulling us to the right, and then we have a negative Ftx pulling us to the left. And so we want to get Ft2, right? And so we know that Ft2 must equal ftx. But we don't know ftx. So what we can do, though, is we can relate ftx to fty using this top angle here. We know this is still 30 degrees. And so we want to relate ftx to fty. Ftx is opposite the angle, while fty is adjacent to it. So that's going to use the tangent relation. I can use tangent of 30 is equal to my opposite over adjacent. Let's see. And so we probably want to get ftx on its own. So we'll multiply both sides by fty. So we get fty times the tangent of 30 is equal to ftx. So we can plug this in down here. We know this is now equal to fty times the tangent of 30. And now we just want to get fty, but fty is going to equal fg, because we can just add fg to both sides here. Because these are balanced, they have to be equal and opposite. So, yeah, we can then plug that in there. Our fg is really mass times gravity, mg. We'll use a big M just because why not? Why not? Mg times the tangent of 30 is equal still to ft2. This is what we're solving for. That's our horizontal tension. And we know values for these. This is 1.8 kilograms times 9.8 meters per second squared times the tangent of 30, which I will have to check on a calculator, but it's probably going to be easy enough that I'll feel silly about it. And so I'm just going to plug in the whole thing as we go here, and we get a magnitude for our ft2. Technically, I guess we could leave it like that, but I wouldn't. It's equal to 10.18. And that is going to be in newtons. That's what this equals to. Good. Any questions on that? No. Looks pretty good. Alrighty. Well, that was actually all we really had to cover today for dynamics. Thank you guys for following me along. I hope you guys learned something. Feel free to reach out to me on my website at 314 Education. I'll be taking questions. You can email me. I do occasional write-ups. We're not doing those as regularly now that we're moving in towards AP season. We're kind of migrating our efforts towards this type of content. Follow us on Instagram. We're at 314education.com. We might be doing some giveaways soon, which will be exciting. We're continuing our series this Sunday. We're going to be continuing every Thursday and Sunday until the last one, which will be the day before the test on a Tuesday. But so next Sunday at 5 p.m. Pacific time, same time as always, we'll be going over the next unit, which will be centripetal motion. Well, that's all I have for you guys. Until the next time, you take care, you keep safe, and I will see you next time. Take care.